Exponential growth and decay is about taking exponential functions like we've been talking about and applying them to real-world problems. So here we have an economics problem. Since 2005, the amount of money spent at restaurants in the United States has increased about 7% each year. In 2005, about $360 billion was spent at restaurants. So in writing a function for this, the first thing we want to do is sort of define our variables. We're going to write a function in terms of f of x. So f of x is going to be the amount spent in a year. And therefore x is going to be years. So with that in mind, f of x is going to be equal to the 360 we started with plus, times, because we're increasing by a factor of 7%, times 1.07 to the power of x, x being the number of years that pass. And you might ask, okay, but where does the 1.07 come from? That's what I don't understand. Well, let's pause for a second on this problem and look at that separately. If we start off with $360 and we want to add 7% to that each year, well, that means we don't want just 7% of that number. We want all of that number, 100% of that number, plus an additional 7% of that number, meaning each year we want 107% of that number. So 107% as a decimal turns into 1.07. And if we want to increase by that much each year, that means the first year we're going to multiply by it once, the second year we're going to multiply by it twice. The third year we're going to multiply by it again, and repeated multiplication means exponents. So that's where we get that x exponent. So that's where that 1.07 is coming from. It's coming from the idea that we want 100% of the 360 plus an additional 7%. So now let's go back to our original problem. The question was, moving forward, if the trend continues. So this question isn't on here, but the question that we want to ask ourselves is if the trend continues, about how much will be spent in restaurants by 2015. Well, that's 10 years later. So we're going to be plugging in 10 for x. Which looks like this. F of x is equal to 360 times 1.07 to the 10th power, which if we do on our calculators gives us about 708 billion. Okay. Good. Another example of exponential growth and decay is something called compound interest. This is how interest is really calculated. We've talked about simple interest before, which is a simple way of calculating interest. That's the I equals PRT. Well, that's not really how interest is calculated. Interest is calculated like this. A, which is going to be the balance of an account, is equal to P, which is the same P as before. That's the principal. That's the initial deposit, times 1 plus the ratio of your annual interest rate divided by the number of times that is compounded per year. Raised to the power of the number of times it's compounded per year over the course of t years. Okay, so there's a lot of moving parts in there, and generally the ends aren't going to play a big role, right? We don't talk a lot about problems where it's compounded multiple times a year. Usually we're talking about compounded once a year. But if it is compounded more than once a year, you need to include this end value. This end value is how many times per year is it compounded. So that's the general formula. Let's look at a problem. So here's our problem. Suppose that when your friend was born, your friend's parents deposited $2,000. This idea of our friend's parents deposited, initial deposit, that's going to be your principal right there. In an account paying 4.5 interest per year, there's your interest rate right there. Okay, compounded quarterly. Okay, this is where that number does come in. Compounded quarterly. Quarterly means 4 times a year. What would the account be after 18 years? And there's your time. So, if I'm going to set up this equation, remember what it looks like. A is equal to principal P, so in that case it's $2,000, times 1 plus the interest rate, but that's a percentage. Remember, we have to write that as a decimal. 0.045 divided by how often per year, which is 4 times, to the power of 4 times 18. Okay? So now we can simplify this. A equals 2,000. 1 plus, we can actually simplify that, and we can just do that on our calculators to get the decimal. 1 plus 0.045 divided by 4 gives us 1.01125, and we're going to raise that to the 4 times 18 power, which again we can simplify to 72nd power. Okay? All right, so once we have that, you can do your 1.01125 to the 72nd power, which gives you this number, 2.237765081, and you're going to multiply that by 2,000. Now remember, at the end of the day, we're talking about dollars, so there is going to be some rounding going on here. And we end up with the amount in the account is $4,475 and about 53 cents. So this is obviously a rounded answer, and it's a rounded and inexact answer, and that's after 18 years. Okay, you're going to have some numbers here that aren't going to be terribly pretty. That's okay. Just use the decimals until the end, and at the end you can go ahead and round to get something that makes sense. Like if we're dealing with money, as we are in this case, rounding to 2 decimal points makes sense. One final point is about exponential decay. Understanding that our functions are going to be essentially in this form, f of x or y equals a times b to the x power. Decay is going to occur when b is less than 1. So anytime b is less than 1, you're going to end up with exponential decay. And that's that graph where it looks like this, right? When you have this sort of thing going on. So that's going to be exponential decay. So look out for those instances where your decay factor, your b, is less than 1. Greater than 0 still, right? We know it's going to be greater than 0, but less than 1.